The research on the triangular grid billiards system examines the relationship between the perimeter of the polygon and the number of different trajectories. It involves a lattice of equilateral triangles, where laser beams are emitted from the midpoint of each grid cell's side into the interior at a 60-degree angle. The direction of the beam depends on the orientation of the side, making either a 60-degree, 180-degree, or 300-degree angle with the positives axis. The light travels through the interior until it reaches the midpoint of another boundary pane, defining a permutation of the grid cells. This permutation, called the billiards permutation, is crucial for understanding the number of trajectories. The authors prove the sharp inequality CYC, P, is less than or equal to perim, P, plus 2, 4, resolving a conjecture by Defant and Jiradilok. The billiards permutation can be viewed as a billiards process, where light beams reflect off mirrors forming a 60-degree angle. Each cycle corresponds to different beam trajectories, with each eye appearing in exactly one cycle and each cycle having a length of at least 3. This concept is rooted in dynamical systems and recreational mathematics, with Defant and Jiradilok's framework imposing rigidity, leading to new combinatorial and geometric questions. The paper focuses on the relationship between the perimeter of a grid polygon and the number of cycles in its associated permutation. It proves the conjecture that the number of cycles is bounded above by 1/4 the perimeter plus 2, and provides a partial characterization of equality cases, including the existence of an infinite family of equality cases given by trees of unit hexagons. Researchers have introduced a novel class of combinatorial objects called membranes, which are dual to Plabic graphs and generalized grid polygons. Focusing on minimal membranes of type A2, referred to as generalized grid polygons, they aim to prove an analogous inequality for this class. The motivation behind considering these objects lies in their potential to drop a cycle from the billiards permutation of a grid polygon, possibly resulting in a non-simple polygon. The paper is structured into 3 sections. The first section establishes the foundation for generalized grid polygons, developing necessary infrastructure around these objects. The second section presents the proof of the generalization of Theorem 1.2 for generalized grid polygons. This proof builds upon the established infrastructure and provides a crucial step towards understanding the properties of these objects. The third section discusses future directions and open problems in the field, highlighting potential avenues for further research. The authors acknowledge the support of various organizations, including Jane Street Capital, the National Security Agency, and the Cyan Undergraduate Mathematics Fund at MIT, which enabled this research opportunity. Additionally, they express gratitude to Joe Gallion and Colin Defant for organizing the Duluth REU and to Mitchell Lee for his contributions to the project. Simplicial complexes are a fundamental concept in topology, consisting of a set of vertices and a set of finite non-empty subsets of vertices called simplices, where any non-empty subset of a simplex is also a simplex. The dimension of a simplicial complex is defined as the largest dimension of any simplex within it. A d-dimensional simplicial complex is considered homogeneous if every simplex is a face of some d-dimensional simplex. In this context, a generalized grid polygon is defined as a finite, simply connected, two-dimensional, homogeneous simplicial complex with a simplicial map to the triangular grid. This complex must satisfy certain conditions, including having a geometric realization that is a wedge of disks along boundary points, mapping each simplex to a simplex of the same dimension in the triangular grid, and adhering to specific vertex and simplex configurations. and the construction of paths that avoid certain cycles while staying within the polygon's interior. In the context of generalized grid polygons, the authors introduce the concept of precomponents. These are pieces that can be inductively cut from an indecomposable polygon P to form the components of a new polygon Q, obtained by removing cycles C1, Ca. The precomponents are denoted as P1, Pk, with P1 corresponding to an outermost component of Q. The sequence of precomponents is not unique and depends on how P is cut. The properties of these precomponents are discussed, particularly in relation to the cycles C1, Ca. It is emphasized that if a pane is on the boundary of a precomponent but not on the boundary of P, it is crossed only by the cycles C1, Ca. This property is crucial for understanding the structure of the precomponents and their interaction with the cycles. The authors also introduce lemma 3.3, which provides a lower bound on the number of boundary panes of P inside a precomponent P1 that are hit by the cycles C1, Ca. This lemma is essential for the proof of theorem 3.1. The proof involves considering the shortest grid path of length k is greater than or equal to 2 on the boundary of P1 but not on the boundary of P, showing that the number of boundary panes of P inside P1 hit by the cycle C1, Ca is at least k plus 2. A detailed analysis is presented for the case where the path is straight and horizontal, including a visual representation in Figure 17. The authors defined two sets of boundary panes U1, UK and V1, Vk hit by the northeast and northwest beams from the panes P1, Pk, respectively. The distinctness of these sets is established, and it is shown that V1 must be distinct from U1, UK. This section provides a comprehensive exploration of precomponents and their properties in generalized grid polygons, laying the groundwork for the subsequent proof of theorem 3.1. In this section, the authors delve into the maximum number of cycles in triangular billiards, employing a contradiction argument to demonstrate that there must be at least k plus 2 distinct boundary panes hit by the beams C1, Ca. They consider two cases. One where the path consists of panes going in the 180 degrees and 240 degrees directions, and another where the path has panes going in the 0 degrees and 120 degrees directions. First, they examine the case where the path consists of panes going in the 180 degrees and 240 degrees directions. Each pane in this path has a beam going in the northwest direction. The authors introduce chi to represent the boundary panes hit by these beams, and W1 and W2 to represent the boundary panes hit by the beams going west and northeast from the first and last panes in the path, respectively. Through Figure 19, they illustrate the impossibility of W1 or W2 being equal to any of the chi, thus establishing that all these panes are distinct. Next, the authors show that W1 and W2 cannot be equal to any of the chi. This is achieved by leveraging lemma 3.2, which states that a pane adjacent to the path cannot be hit by C1, Ca. Since W1 and W2 are both adjacent to the path, they cannot be equal to any of the chi. Consequently, it is concluded that there must be at least k plus 2 distinct boundary panes hit by C1, Ca, as shown in Figure 19. This result significantly contributes to the understanding of the maximum number of cycles in triangular billiards, providing a crucial step in the proof of the main theorem. The use of contradiction in geometric reasoning allows the authors to establish a lower bound on the number of distinct boundary panes hit by the beams, further elucidating the properties of these systems. The authors initiate the proof of theorem 3.1 for the simplest polygons, which exclusively contain 3 cycles in their billiards permutation. They introduce lemma 3.4, stating that if an indecomposable generalized grid polygon's billiards permutation contains only 3 cycles, then it is either a unit triangle or a unit hexagon consisting of 6 unit triangles, as depicted in Figure 20. The proof of lemma 3.4 involves demonstrating that if a polygon contains more than 3 cycles, then at least 2 of these 3 cycles have the same orientation. By applying theorem 2.5, the authors can sequentially remove all the 3 cycles except for these 2, resulting in an indecomposable generalized grid polygon of perimeter 6 with 3 cycles of the same orientation. They then demonstrate that none of the 15 possible boundary loops can admit a cycle structure with 3 cycles of the same orientation, thereby proving that any indecomposable generalized grid polygon containing only 3 cycles contains at most 2 3-cycles, and if it contains exactly 2, they must have opposite orientation. Next, the authors bound the number of components that an indecomposable generalized grid polygon can have after removing several cycles. They introduce proposition 3.5, which states that if Q is obtained by removing cycles of total length m from an indecomposable generalized grid polygon P, and P1, Pk are the precomponents of Q, then 2kt is less than or equal to m2, where T is the number of triangular precomponents. Furthermore, if P is primitive, then equality holds if and only if m is less than or equal to 4. The proof of proposition 3.5 involves induction on m. The base case, where m equals 3, is handled using lemma 3.2, which implies that k equals t equals 1. The authors then proceed to the inductive step, where they consider a sequence of precomponents P1, Pk of Q if P1 is a triangular precomponent, then letting P be P with the outermost component removed, they can apply the inductive hypothesis to P. The authors complete the proof of lemma 3.4 by considering 2 cases: when P1 is a triangular precomponent and when it is not. In the first case, they apply the induction hypothesis to show that the desired inequality holds. In the second case, they suppose P1 is not triangular and intersecting with P forms a path of length L, and then use lemma 3.3 to bound the number of panes incident to C1, Ca in P1 and P. This leads to the desired inequality. The authors then prove theorem 3.1 by induction on the perimeter of P, considering the billiards permutation pi of P. If pi contains only 3 cycles, the inequality follows from lemma 3.4. If pi contains an m cycle C with m is greater than or equal to 4, they remove C to obtain a generalized grid polygon Q and decompose Q into precomponents P1, Pk. By the induction hypothesis, they bound the number of cycles in each chi and then combine these bounds to obtain the desired inequality for CYC, P. The proof relies on proposition 3.5 and the previously established bounds on the number of cycles in triangular precomponents. The authors use these results to show that CYC, P, is bounded above by 1/4, perim, P, plus 2, completing the proof of theorem 3.1. Future directions in combinatorial billiards. This section delves into the future directions of combinatorial billiards, focusing on the study of billiard systems in different grids, polygonal regions with holes, and connections with Plabic graphs. A key area for further research is the full classification of primitive equality cases, particularly those containing exactly 2 3-cycles and no cycles of length greater than 4. The concept of generalized grid polygons and their one-skeletons is introduced, connecting to the study of cacti and membranes of type A2. The latter includes minimal membranes, which are viewed as simply connected simplicial complexes. These minimal membranes have potential implications for understanding the properties and behaviors of billiard systems within these complex geometric structures. The section concludes with a conjecture regarding billiards permutations on minimal membranes of type A2, stating that the number of cycles does not exceed 1 plus the perimeter and twice the number of components. This conjecture, if proven, could provide significant insights into the combinatorial properties of billiard systems in these contexts, shedding light on their underlying structure and dynamics. The relationship between billiards permutations and membranes, particularly in the context of Plabic graphs, is a significant area of study. A key result states that if a polygon's permutation contains exactly 2 3-cycles and no cycles of length greater than 4, then the maximum number of cycles in its triangular billiards is calculated as 1 plus 4 times the perimeter plus 2. This result applies only to indecomposable and primitive polygons, excluding single edge cases. Defant and Jiradilok's work on strand permutations of Plabic graphs serves as motivation for studying dual objects like billiards permutations and membranes. Their research has led to a simpler proof for a result, which shows that the maximum number of cycles in a simple grid polygon is less than or equal to 1 plus 6 times the area plus 1, with equality holding if the polygon is a tree of unit hexagons. This proof is generalized for more complex polygons and utilizes a lemma to reduce the inequality to the case of indecomposable and primitive polygons. In conclusion, the use of Theorem 2.5 for inductive proof on the area of the polygon demonstrates that any indecomposable primitive generalized grid polygon with more than one cycle satisfies the inequality strictly. This highlights the importance of studying billiards permutations and membranes in the context of Plabic graphs, as it can provide insights into the structure and properties of these complex geometric objects. The research paper focuses on triangular billiards, specifically on the maximum number of cycles when k, the number of precomponents, is greater than or equal to 2. It establishes that for k equals 1, the only cycle with area, c, is less than or equal to 6 is a 3-cycle in a unit hexagon. For k is greater than or equal to 2, any cycle c has area, c, greater than 6, using properties of precomponents and corresponding cycles along with proposition 3.5 and lemma 3.3. The paper then generalizes Theorem 1.2 and Theorem 4.4 for grid polygons with holes, introducing conjecture 4.5, which proposes an upper bound for the number of cycles in such polygons. An example of a grid polygon with holes serves as an equality case for conjecture 4.5, as depicted in Figure 21. Conjecture 4.6 proposes an upper bound for the maximum number of cycles in triangular billiards, stating that for a grid polygon with holes, the maximum number of cycles is less than or equal to 1/6 of the area of the polygon plus the number of holes plus 1. This bound has implications for the study of minimal membranes of type A3, which are cactus graphs equipped with a map to the A3 root lattice. The authors suggest exploring analogues of Theorem 1.2 and Theorem 4.4 for these membranes, involving the definition of billiards permutations on membranes of type A3 from strand permutations on the dual Plabic graphs. However, a natural geometric interpretation for these billiards permutations remains an open problem. Another direction for future research is to investigate the properties of the set of billiards permutations directly. For instance, it is observed that the permutation 1 3 2 4 is not the billiards permutation of any generalized grid polygon, leading to question 4.7, which seeks a characterization of the subset of permutations that appear as the billiards permutation of some generalized grid polygon.